The outcome that we are going to look at is set theory. The essential question for this outcome is why is set theory important? And as we go through the lesson for this outcome, hopefully you will see why it is important to have set theory. What do you think about these statements? We want you to decide whether you agree or disagree, and then explain your decision. If you were to sort the letters of the alphabet, you can only use two categories, vowels and consonants. Do you agree or disagree with that statement? Number two, you cannot always count how many things are in the category. Do you agree or disagree with that? And if 5 people belong to Club A, 7 people belong to Club B, and 8 people belong to Club C, then there is a total of 20 people who belong to these clubs. Do you agree or disagree? Now, we're not going to discuss the answers at this point in time. These are things that you are going to learn over the course of the next few lessons. And hopefully you will be able to come back and reflect on these and see if your answers still stay the same or if you would like to change what you think about these statements. So in this first lesson, we're going to look at types of sets and set notation. And our goal is to understand sets and set notation. What are they? So here's a question for you. What categories can you use to organize your closet? So you think your closet is your bedroom closet. How can you organize your closet? And there's many different possibilities we could talk about. Maybe we organize them and put shirts in one area, pants in another, dress clothes, casual clothes. You could organize summer clothes, winter clothes. You could organize by color. There's lots of different ways that you can categorize and organize your closet. Some terminology we need to discuss that is very important to this outcome. Set is a collection of distinguishable objects. For example, the set of whole numbers is W equals 0, 1, 2, 3, dot, dot, dot. So it would continue. So that's the set of whole numbers. All of the objects that are in that particular set. An element is an object in a set. For example, 3 is an element of D, which is the set of digits. Digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 3 is one of the objects in that set, so we call it an element. A universal set is a set of all the elements under consideration for a particular concept. This can also be called the sample space. For example, the universal set of digits is D equals 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's the entire set when we're talking about digits. So we call that the universal set. The complement is all the elements of a universal set that do not belong to a subset of it. For example, if we say the complement is O, and we denote that with this little apostrophe mark up there. That's what we use to denote complement. So if we have the complement of O is 0, 2, 4, 6, 8, is the complement of subset O, which is 1, 3, 5, 7, 9, which was a subset of the universal set of digits. So the complement is denoted with the prime sign, 0, and then that little apostrophe. So what we're saying is if we have a set of digits, 0 to 9, and we have a set of it, 0 equals 1, 3, 5, 7, 9. So if we're taking this as a subset of the universal, 1, 3, 5, 7, 9. The complement of that is everything that's in the universal set. So when we're thinking about all of the digits, the complement is those that are not in the set 0. So the 0, 2, 4, 6, 8. These are the complement because they are the parts that were not in the subset we were talking about. We will do a number of examples with this, so that hopefully you will catch on to what we need to do. Empty set is a set with no elements. For example, the set of odd numbers divisible by 2 is the empty set. There are no odd numbers that are divisible by 2. The empty set is denoted by two sets of brackets with nothing in them, or the zero with a line through it. Disjoint. Two or more sets having no elements in common. For example, the set of even numbers and the set of odd numbers are disjoint. So there's nothing common to both of them. Alright, so let's look at some of the notation that we need to know for sets. Sets are defined using brackets. For example, to define the universal set of numbers 1, 2, and 3, we listed elements u equals. And notice for the curly bracket, 1, 2, 3. Right? So when you're defining a set, you use the bracket. To define the set A that has the numbers 1 and 2 as elements, we write it as A equals 1, 2, and we use the curly bracket. All elements of A are also elements of U, so A is a subset of U, and this is the symbol for subset. So A is a subset of U because everything in A was the number 1 and 2, are also in U, which was 1, 2, and 3. So we call that A is a subset of U. The set A prime is the complement of A, and we can define it as A prime equals 3. Because if we think the universal set was 1, 2, 3, A was just 1 and 2, so what's left over? Just 3, so that's the complement. To define the set B, a subset of U that contains the number 4. Now if we look at U, there was no 4 in there. So what we're saying is B is actually the empty set. So we can denote it either using brackets with nothing in it, that symbol, and we can say that B is a subset of U. It's an empty set, so it is a subset of U. The phrase from 1 to 5 means from 1 to 5 inclusive. So it means 1, 2, 3, 4, and 5. So if that's what you read in a question or a situation, it means all of the numbers between 1 and 5. In set notation, the number of elements of the set X is written as n bracket X. So the number of elements in X. For example, if the set X is defined as the set of numbers from 1 to 5, X equals 1, 2, 3, 4, 5, and the number of elements in X is just 5. That doesn't mean that the number 5 is necessarily in the set. In this case, it is. But what this means is that how many elements were in the set. Finite set. A set with a countable number of elements. For example, the set of even numbers less than 10 are simply 2, 4, 6, 8. It's a finite set because we can actually count how many are in that set. Whereas an infinite set is a set with an infinite number of elements. For example, the set of natural numbers, 1, 2, 3, dot, dot, dot. Because natural numbers will continue on to infinity. So that is an infinite set. We can't count them. This might take you back to one of those first questions that I asked you to agree or disagree on. You cannot always count how many things are in a category, and whether or not you agree or disagree with that question. Now you should be able to see that we can't always count how many elements are in a set. Mutually exclusive is when two or more events that cannot occur at the same time. For example, the sun rising and the sun setting are mutually exclusive events. They do not happen at the same time. So let's look at this example. Brooke drew the following Venn diagram. Brooke described the sets as follows. She said that C represents product. F, and in the Venn diagram, F is the orange oval. F defines fruit. S, that's in the small green circle. S defines the fruit that you can eat without peeling. And B, which is the green oval, defines vegetables. And then she's got elements listed in each of these sets. Do you agree with her description? Do do you agree that they all fit? Is everything that's listed in this rectangle, so in this Venn diagram, do you agree that it's all produce? Because that's what she's saying that C is, it's produce. And because C is written up in the little corner here, out of the way, there's no circle with it, we're saying that that's the universal set. So if we look through everything, yes, they're all produce. So that part's okay. F, she's defining as fruit. So if we look in that orange oval, oranges, pineapples, bananas, apples, and pears, those are all fruit. S is fruit you can eat without peeling. Well, you can eat apples and pears without peeling, but you need to peel oranges, pineapples, and bananas. So yeah, that makes sense. And B is vegetables. Peas, carrots, potatoes, corn, and beans. Yes, those are all vegetables. So her descriptions are accurate. We want to describe another way for us to find the sets of the diagram. So this is just to show you that there's more than one way to categorize things. Remember back when we talked about categorizing your closet. You can categorize them by the types of clothing. You can categorize them by color, by season. So just like she categorized the produce here and separated into fruits and vegetables, there is other ways that you can do this. So think about another way you might categorize it. And again, there's more than one possibility. Maybe she chooses to do this. See if children produce. But now, I'm going to categorize them by color. I'm going to be, O is going to be orange color. And so therefore, if it's orange produce, my elements would be oranges and carrots. Because those are orange in color. Then I'm going to have Y is going to represent yellow color. And if I look to see what we have as yellow, we've got bananas, we've got pineapple, and we've got corn. All of those are yellow produce. We also have produce that is green. So I'm going to have another category that is green produce. And if we look at what is green, well, apples could be green. Peas are green. And we can have green. B is going to represent my brown produce. And if we look and see in here what is brown, well, we can have potatoes. And we can have carrots. So it's just another way that we could categorize it. And again, there's other ways. You might have thought of something different. But just to show you that there's more than one way to categorize a set. C. Why does it make sense that we say S is a subset of F and F is a subset of C? Now remember what a subset means. It means every element that's in the set is also in the set of the larger one. So if we're saying F is a subset of F, all of the elements of F must also be in the set F. So F is a subset of F. Makes sense because if we look here, apples and pears are also in our set F, which is fruit. And F is a subset of C. S is apples and pears. C is all of your produce. Apples and pears are produce. So it makes sense that they are subsets of the others. D. List the disjoint sets if there are any. Now remember, disjoint means they have no elements in common. So if we look at this, fruits and vegetables are two totally distinct sets. So they are called disjoint. Fruits and vegetables are disjoint. There is no common element in them. We could also say X and Z are disjoint. Because F is our fruit that you can eat without peeling, and B is our vegetables. There are no common elements in either of those sets. complement of F, so is F prime equal to V? And explain. Remember, the complement is when you take the entire universal set, so in this case, all of our products, and we look at set F. F is the fruit. So if the complement of that, the complement would be everything in that universal set that is not fruit. Does that happen to all be vegetables? And in this case, yes it is. So yes, the complement of F, or F prime, is equal to V. We want to determine how many elements are in V. So how many vegetables do we have? Using the number of fruits and the number of our universal set. Now some of you are just going to count that up and go, hey, there's 5 elements. And you're absolutely right. If we're using the Venn diagram, and we just count our number of vegetables, there are 5 of them. We can also use this though by understanding how many are in the set F and the set G. So in our universal set, there are 10 pieces of product that we have, and in our fruit, we have 5 pieces. So 10 minus 5 leaves us with 5 elements in the vegetable. List the elements in F prime. So what's the complement of F? Remember, F is just apples and pears. So the complement is everything that is not apples or pears. So we would have oranges, we'll have pineapples, we will have bananas, peas, carrots, potatoes, corn, and beans. So it's all of the elements in the entire set, so in our C, that were not in F. Alright, let's have a look at another one here. We want to now draw a Venn diagram. So in the last example, the Venn diagram was given to us, but now we want to draw it. So, we want to make sure that we make it large enough so that we can fit everything that we might need in it. The universal set is the natural numbers from 1 to 40. So we're looking at all of the numbers from 1 to 40, and we're calling it U. For our universal set, we indicate it up in the right-hand corner, or you put it in the left-hand corner. Somewhere you need to indicate where it goes. Now, E are the number of multiples of 3. So if we think of the numbers from 1 to 40, and we think of the multiples of 3, that's going to form set E. The multiples of 15 are going to form set F, and the multiples of 9 are going to form set F. Now we have to consider, do we have some of these that are subsets of another? And we want to make sure that we incorporate them appropriately. So maybe we'll start with the larger one, the multiples of 15. We're going to call it F. Multiples of 15 between 1 and 40 are just 15 and 30. We're going to see where those end up falling in. Looking at our multiples of 9. So of 9, 18, 27, 36. Those are our multiples of 9. None of those overlap, so they are definitely disjoint sets. Now if we look at our multiples of 3, we've got 3, 6, 9, which we've already written down, 12, 15, which we've already written down, 18 is already written down, 21, 24, 27, which is already written down, 30, which is already written down, 33, 36 is already included, 39. Notice, everything that got put in set F and everything that got put in set F were also multiples of 3. So those sets have to be inside our circle or our oval E. Now we have to look at everything that's left over in our universal set. So we were looking at the numbers from 1 to 40. Only part of them got put in these ovals. So all of the numbers that we missed are 1, 2, 4, 5, 7, 8, 10, 11, 13, 14, 16, 17, 19, 20, 22, 23, 25, 26, 28, 29, 31, 32, 34, 35, 37, 38, and 40. So those ones all get left outside of our sets that we defined. So now that we have our Venn diagram, we can answer some questions. List the disjoint subsets, if there are any. So, you definitely know. Now when we think about the sets that we define, they're all in the ovals. You define F, and you define E. Ones that are disjoint, F and S. Those subsets have no elements in common. But F and E have elements that are common. 15 and 30 are in both sets. If you look at F, its numbers are also in set E. And all of them are in the universal set U. So now we want to look and see if each statement is true or false. Is E a subset of F? And remember, in order for it to be a subset, all elements of E must be in F. That's not the case. Only 2 elements of E are in F. So this is false. 6, for example, 6 is in E, but not F. And there's just one example. Really, it's any of these ones here. That could pick any of those elements. All of those are in E, but they are not in F. Let's look at the second one. Is F a subset of E? Well, here's F. Are all of the elements of F also in set E? And the answer is yes. So this is true. All elements of F are also in E. Is F a subset of F? No. In fact, they're disjoint. We answered that up here. F is not a subset of F. None of the elements of F are in F. Is F a subset of F? Here's something we haven't talked about. The answer is yes. It is. A set is a subset of itself. So it can be, we can actually classify it as a subset of itself. And the last one. Is the complement of F, so is F times all numbers from 1 to 40 except 15 and 30. So what is F? F is the set that contains 15 and 30. So what's our universal set? It's all the numbers from 1 to 40. Remember, the complement is every number that is not in that particular set. So in this case, that's a true statement. F is the element 15 and 30. The universal set are the numbers 1 to 40. So the complement of F is everything from 1 to 40 except 15 and 30.